Hi there, future teacher. Do you need to pass the MTTC Upper Elementary Education Subtest for Science and Social Studies exam? If so, you've come to the right place. In this video, I'm going to walk you through a thorough overview of the exam, and then we'll do a deep dive into the science and social studies content that you need to master for test day. We're active listeners, right? So grab your pen and paper and let's get started. Before we dive in, we put together a free study guide workbook that goes along with this video. It has all the key terms, comparison tables, practice questions, and space for your own notes. Grab your free copy from the link in the description. This video is proudly presented by TeacherPreps.com, where we offer a complete test prep program for the MTTC Upper Elementary Education exam, including study guides, practice tests, and more. Our program is self-paced and free to start. So when you're ready, simply click the link in the description or visit us at TeacherPreps.com. All right, that was our plug. For the rest of this video, it's go time. Grab your pen and paper. Let's begin. Now let's look at the three subareas that make up this exam. Subarea I is science, engaging learners in three-dimensional science learning. This subarea accounts for 25% of your total score and covers objectives 1 through 4. Subarea II is science, learners' sense-making and science teaching pedagogy. This subarea also accounts for 25% of your score and covers objectives 5 through 8. Subarea III is social studies, instruction and practices. This is the big one. Social studies accounts for 50% of your total score and covers objectives 9 through 13. So if you're short on study time, pay special attention to social studies. It's literally half your exam. But of course, we're covering everything today. Let's start with the science subareas. Let's jump into Subarea I, which is all about engaging learners in three-dimensional science learning. Objective 1 focuses on scientific phenomena, and this concept is at the heart of the next-generation science standards approach to teaching science. So what is a phenomenon? A phenomenon is an observable event or situation in the natural world that sparks curiosity and drives scientific investigation. Think of a puddle disappearing on a hot sidewalk, or a bicycle chain turning rusty after being left in the rain. These are everyday phenomena. There are two main types you should know. An anchoring phenomenon is a big, complex event that drives an entire unit of study. For example, why do some areas of the schoolyard have more puddles after rain than others? That single question could anchor a weeks-long investigation into water, soil, and drainage. An investigative phenomenon is a smaller, more focused event used within a lesson to explore a specific concept. For instance, what happens when you place a drop of food coloring into cold water versus hot water? That investigates molecular motion. When you select a phenomenon for your classroom, it needs to meet certain criteria. A productive phenomenon is observable by students, relevant to their lives, complex enough to sustain investigation over time, and it cannot be fully explained by a single Google search. On test day, look for answer options that describe phenomena as student-driven and inquiry-based, not as teacher demonstrations followed by vocabulary lists. Objective 2 covers the 8 science and engineering practices, and these are a central pillar of three-dimensional science learning. Let's tackle the first 4 practices now. Practice 1 is asking questions and defining problems. In science, students ask testable questions about the natural world. For example, a 4th grader might ask, does the amount of sunlight affect how fast a bean plant grows? In engineering, students define problems that need solutions. For instance, how can we design a container that keeps an ice cube from melting for 30 minutes? The key shift here is that students generate the questions, not the teacher. Practice 2 is developing and using models. A model is a simplified representation of a system or process. In grades 3 through 6, students might draw a diagram of the water cycle, build a physical model of an ecosystem food web with yarn and index cards, or create a digital simulation of how erosion changes a landscape. Models help students explain phenomena and make predictions. Practice 3 is planning and carrying out investigations. This means students design their own experiments, identify variables, collect data, and control conditions. A third grader might investigate which type of soil absorbs the most water by pouring equal amounts through sand, clay, and potting soil, then measuring what drains through. A fifth grader might plan a fair test comparing the strength of different bridge designs. Practice 4 is analyzing and interpreting data. Students organize their observations using tables, graphs, and charts, then look for patterns and relationships. A sixth grader might create a bar graph comparing average monthly temperatures across different Michigan cities and notice that cities near the Great Lakes have milder temperature swings. Jot these 4 down. Ask questions, use models, investigate, and analyze data. Now let's cover the remaining 4 science and engineering practices. Practice 5 is constructing explanations and designing solutions. In science, students construct evidence-based explanations for phenomena. A powerful framework for this is CER, which stands for claim, evidence, reasoning. The student makes a claim, supports it with evidence from their investigation, and then provides reasoning that connects the evidence to a scientific principle. For example, a student might write, "My claim is that dark-colored surfaces absorb more heat than light-colored surfaces. My evidence is that the black paper reached 45 degrees Celsius, while the white paper only reached 32 degrees after 20 minutes under the lamp. My reasoning is that darker colors absorb more light energy, which converts to thermal energy." In engineering, students design solutions to problems. The engineering design process goes like this: define the problem, brainstorm solutions, design and build a prototype, test the prototype, analyze the results, and then redesign to improve. A key distinction you need to know: science asks, "Why does this happen?" while engineering asks, "How can we solve this?" Practice 6 is engaging in argument from evidence. Students learn to support or challenge claims using data, not opinions. In a classroom debate, a student might argue that reducing pesticide use would help local bee populations, citing data from a class investigation on pollinator counts in treated versus untreated garden plots. Practice 7 is using mathematics and computational thinking. Students apply math to analyze science data. This includes measuring, calculating averages, creating graphs, recognizing numerical patterns, and using ratios. For example, calculating the average rainfall per month across a school year. Practice 8 is obtaining, evaluating, and communicating information. Students read scientific texts, evaluate the credibility of sources, and communicate findings through writing, presentations, and discussions. A fourth grader might research how animals in different habitats have adapted to survive, then present findings to the class using a poster. All 8 practices work together, and on your exam, look for questions that ask which practice a student is using in a given scenario. Objective 3 covers the disciplinary core ideas, which are the big content concepts that students learn across grades 3 through 6. Let's start with life science and earth science. In life science, there are 4 core idea groups. LS1 is structure and function. Students learn that organisms have internal and external structures that serve specific functions for growth, survival, and reproduction. For example, a plant's roots absorb water and nutrients, the stem transports them, and leaves capture sunlight for photosynthesis. In animals, the heart pumps blood, lungs exchange gases, and bones provide structural support. LS2 is ecosystems, interactions, energy, and dynamics. Students explore food chains and food webs, learning that energy flows from the sun to producers like plants, then to primary consumers like herbivores, then to secondary consumers like predators. They also learn that matter cycles through ecosystems as organisms eat, decompose, and return nutrients to the soil. LS3 is heredity, inheritance, and variation of traits. Students discover that offspring inherit traits from their parents, but variation exists within every population. A litter of puppies might all look different even though they share the same parents. LS4 is biological evolution, unity, and diversity. Students learn that organisms with traits well suited to their environment are more likely to survive and reproduce. This is adaptation. Polar bears have thick fur and a layer of blubber because these traits help them survive in Arctic conditions. Now for Earth science. ESS 1 covers Earth's place in the universe. Students learn about the Earth-Sun-Moon system, including why we have day and night, the phases of the moon, and why seasons change based on Earth's axial tilt. ESS 2 covers Earth systems. This includes weathering, erosion, the water cycle, and the rock cycle of igneous, sedimentary, and metamorphic rocks. Students investigate how water moves through evaporation, condensation, precipitation, and collection. ESS 3 covers Earth and human activity. Students explore how humans use natural resources, the impact of pollution and deforestation, and what individuals and communities can do to protect the environment. Now let's cover the physical science disciplinary core ideas. PS1 is matter and its interactions. Students learn that matter exists in 3 common states: solid, liquid, and gas. Solids have a fixed shape and volume. Liquids have a fixed volume but take the shape of their container. Gases expand to fill any available space. Students also learn about physical changes like melting and dissolving versus chemical changes like rusting and burning. A physical change alters the form of a substance, but not its chemical identity. Ice melting into water is still H2O. A chemical change produces a new substance entirely. When iron rusts, it combines with oxygen to form iron oxide, a different substance. PS2 is motion and stability, forces and interactions. Students investigate how forces cause objects to speed up, slow down, or change direction. Gravity pulls objects toward Earth. Friction slows objects down. Balanced forces result in no change in motion, while unbalanced forces cause acceleration. A classic grades 3 through 6 investigation is testing how ramp height affects the distance a toy car travels across the floor. PS3 is energy. Students learn about different forms of energy. Kinetic energy is the energy of motion. Potential energy is stored energy based on position or condition. Thermal energy relates to heat, and light and sound are also forms of energy. Energy can transfer between objects. When you strike a drum, kinetic energy from your hand transfers to the drumhead, which vibrates and produces sound energy. PS4 is waves and their applications in technologies. Students explore how waves transfer energy without transferring matter. Sound waves travel through air as vibrations. Light waves can be reflected, refracted, or absorbed. A prism separates white light into a spectrum of colors because each color has a different wavelength and bends at a slightly different angle. The key teaching principle for all of these core ideas: teach them through phenomena, not through vocabulary lists. Instead of defining kinetic energy on the board, have students observe a pendulum and ask them to explain when the ball is moving fastest and when it seems to pause at the top of its swing. Objective 4 covers the crosscutting concepts, which are the thinking lenses that connect ideas across all science disciplines. There are 5 you need to know for this exam. The first is patterns. Scientists look for patterns in data and nature. Students might notice that most flowering plants bloom in spring, or that the moon's appearance follows a predictable cycle every 29 days. Recognizing patterns helps students make predictions. The second is cause and effect. Students learn that events have causes, and scientists design experiments to test those cause and effect relationships. If we add fertilizer to one set of plants, but not another, we can determine whether the fertilizer caused any difference in growth. The third is systems and system models. A system is a group of interacting parts that form a whole. The human body is a system. An ecosystem is a system. The water cycle is a system. Students use models to understand how parts of a system work together and what happens when one part changes. The fourth is scale, proportion, and quantity. Some phenomena are too large or too small to observe directly. The solar system is too vast to see all at once, while cells are too tiny to see without a microscope. Students use scale models, mathematical ratios, and measurement to understand phenomena at different scales. The fifth is energy and matter, flows, cycles, and conservation. Students track how energy flows and matter cycles through systems. In a food web, energy flows from producers to consumers, while matter like carbon and nitrogen cycles between living organisms, the atmosphere, and the soil. These cross-cutting concepts are powerful because they apply across life science, earth science, and physical science. When you plan a lesson, ask yourself, which cross-cutting concept can my students use to make sense of this phenomenon? That integration is exactly what three-dimensional science learning looks like. Let's test your understanding with a practice question for Subarea I. Here's the scenario. A fourth-grade teacher wants to begin a new science unit on weather and climate. The teacher is selecting a phenomenon to anchor the unit. Which of the following would be the most effective anchoring phenomenon? Option A, showing students a diagram of the water cycle from the textbook and asking them to memorize the steps. Option B, telling students that warm air rises and cool air sinks, then having them take notes. Option C, asking students why it rained heavily last Tuesday but was sunny and dry the rest of the week, and using that question to drive the unit's investigations. Option D, having students read a chapter about weather instruments and then answer comprehension questions. Take a moment to think about your answer. The correct answer is C. An effective anchoring phenomenon is observable, relevant to students' lives, and complex enough to sustain investigation over multiple lessons. Asking why last week's weather varied is something students personally experienced, and it naturally leads into investigations about air masses, precipitation, temperature, and the water cycle. Options A, B, and D describe teacher-directed activities that skip the inquiry process entirely. Now let's move into Subarea II, which focuses on how to actually teach science using the three-dimensional approach. Objective 5 is about evaluating and modifying instructional materials to support three-dimensional learning. Here's the reality. Many existing textbooks and curriculum resources were written before the current framework was adopted. They often present science as a collection of facts to memorize rather than a process of investigation and sense-making. Your job as a teacher is to evaluate those materials critically. Ask yourself, does this lesson engage students in at least one science practice? Does it connect to a disciplinary core idea? Does it apply a cross-cutting concept? If a textbook lesson on magnetism simply defines magnets and lists their uses, you can modify it by adding an investigation where students test which materials are attracted to magnets and which are not, then construct explanations using the CR framework. You should also look for cross-disciplinary connections. Science connects naturally to mathematics through measurement, data analysis, and graphing. It connects to English language arts through informational reading, scientific writing, and argumentation. And it connects to social studies through topics like natural resources, human impact on the environment, and the history of scientific discovery. When you see exam questions about modifying curriculum, choose the answer that adds student investigation and removes passive reading. Objective 6 is about how learners make sense of scientific phenomena. Sense-making is the process through which students build understanding by connecting new experiences to what they already know. It is not about getting the right answer. It is about developing explanations that make sense to the student. Students make sense of phenomena through multiple modes. Speaking, students discuss observations with partners and share ideas in class discussions. Writing, students record observations, draft explanations, and revise their thinking in science journals. Drawing, students sketch diagrams, label parts of systems, and create visual models of processes they observe. Physical models, students build three-dimensional representations using materials like clay, blocks, or craft supplies. Physical enactment. Younger students might act out the water cycle by pretending to be water molecules moving through evaporation, condensation, and precipitation. When you elicit student ideas, you can do it at different scales. Individual sense-making might look like a journal entry where each student writes their initial explanation of a phenomenon before any investigation. Small group sense-making involves partner discussions or lab teams sharing observations and building consensus. Whole class sense-making happens during discussions where the teacher facilitates and students compare their explanations, notice contradictions, and work toward a shared understanding. The critical shift here is moving beyond correct versus incorrect. A student who says plants eat dirt to grow has a productive starting idea. Instead of correcting them immediately, guide them toward investigations that help them revise their own thinking. Objective 7 covers culturally relevant science pedagogy, inclusive practices, and assessment. Culturally relevant teaching means connecting science instruction to students' cultural backgrounds, home experiences, and community knowledge. Every student walks into your classroom with funds of knowledge, which are the skills, experiences, and understandings they've gained from their families and communities. A student whose family gardens has practical knowledge about soil, seasons, and plant growth. A student whose family fishes understands weather patterns, water ecosystems, and animal behavior. Your job is to recognize and leverage these experiences as entry points for learning. Building an inclusive linguistic culture means creating a classroom where every student feels comfortable sharing ideas. Use structured conversation strategies. Think Pair Share gives every student time to formulate ideas before speaking publicly. Sentence frames like "I observed that" or "my evidence" shows support students who are building academic language, including English language learners. Partner talk allows students to rehearse explanations in a low-stakes setting. Agree and disagree protocols teach respectful scientific discourse. "I agree with your claim because," or "I see it differently because my data shows." For assessment in a three-dimensional science classroom, use both formative and summative approaches. Formative assessments happen during instruction, exit tickets, science journal checks, observation checklists, and classroom discussions. Summative assessments measure what students have learned at the end of a unit. But both types should assess all three dimensions. Can the student use a practice, apply a core idea, and think through a cross-cutting concept? A traditional multiple-choice test that asks "define photosynthesis" only assesses content recall. A three-dimensional assessment asks students to construct an explanation for why a plant placed in a dark closet stopped growing. Objective 8 focuses on equity and access in science education. Equity in the science classroom starts with asking critical questions. Who benefits from this lesson, and whose perspectives are missing? Are some students consistently being excluded from participation? Whose ideas are valued in class discussions, and whose are overlooked? Every student deserves access to rigorous, meaningful science learning. This means ensuring that English language learners have visual supports, sentence starters, and hands-on materials that don't require fluent English to participate. It means providing accommodations for students with disabilities without lowering the cognitive demand of the task. It means representing diverse scientists in your curriculum, so students of all backgrounds can see themselves in the field. Highlight scientists like Mae Jemison, the first African-American woman in space; Mario Molina, the Mexican chemist who discovered the ozone layer crisis; and Qianxin Wu, whose experiments on particle physics changed our understanding of fundamental forces. Community assets are another powerful equity tool. Invite family members to share expertise related to science topics. A parent who works in agriculture can contribute to a unit on plant growth. A community member who monitors water quality at a local river can support investigations on ecosystems and pollution. Productive struggle is also important. Resist the urge to rescue students from confusion too quickly. When students grapple with a challenging phenomenon, they build deeper understanding. Your role is to provide just enough scaffolding to keep them engaged without doing the thinking for them. Here's a practice question for Subarea II. A fifth-grade teacher is reviewing a textbook lesson on states of matter. The lesson defines solids, liquids, and gases, provides examples of each, and ends with a worksheet where students match definitions to terms. The teacher wants to modify this lesson to align with three-dimensional learning. Which modification would be most effective? Option A: adding a video about states of matter for students to watch before completing the worksheet. Option B: replacing the worksheet with an investigation where students observe what happens when they heat butter in a pan and freeze orange juice in a cup, then use evidence to explain how heating and cooling affect the state of matter. Option C: giving students additional vocabulary terms about plasma and Bose-Einstein condensates. Option D: having students copy the definitions from the textbook into their science notebooks. The correct answer is B: replacing the worksheet with a hands-on investigation where students observe real phenomena and construct explanations using evidence transforms the lesson into a three-dimensional experience. Students use the practice of constructing explanations, the core idea of matter and its interactions, and the cross-cutting concept of cause and effect. The other options keep learning passive and fact-based. Great work making it this far, future teacher. In this video, you covered Subarea I, engaging learners in three-dimensional science learning, and Subarea II, sense-making, and science teaching pedagogy. Together, that's 50% of your exam. But here's the thing. Subarea III, social studies instruction and practices, is the other 50% of your score. That means the 5 social studies objectives covering civic engagement, history, geography, civics, and economics are half your entire exam. To pass, you need all 3 subareas. Get the complete study guide covering all 13 objectives, plus full-length timed practice tests at TeacherPreps.com. Link is in the description. If this video helped you, click the like button and subscribe for more study guides. Best of luck on your upcoming exam.